All right, we're taking a look at domain and range today, along with some other function stuff. So just remember the domain is a set of all x values. So think about like x and y, what comes first, and then domain and range. So x, domain, y, and the range. So the domain of the functions is all the x values. So we can see we're starting here. This is where they're starting, and then it's going forever in that direction. Okay, it includes this point because of the closed circle. So it's all the x values that are greater than or equal to, and then check where it is on the graph, and that's -1. So this would be choice 4. Okay, 478, same thing. We're looking for domain, so it's the x values. It starts here, it includes this point, and it goes forever in that direction. So this is -4. So all the x values that are greater than or equal to -4. Okay, so we want choice 4. All right, which statement is always true? So this is just a line. It's a linear equation. So if f of x is greater than 0, or less than 0, greater than 0, if x is less than 0, okay? So if the easiest way, I think, to do this one is probably also to look at the graph. So hold on. So if we didn't have a calculator, all right, so we got our calculator up here, okay? So we're gonna go new document, okay? We won't save, open a graph, and we're gonna type in that fraction. So 1/3 x plus 9, there's our graph. Remember, if we can't see it all the way, we're gonna go to menu, zoom, and then fit, and there's our graph. So you can see it's decreasing. So what this really means here, okay, and we can kind of zoom out, is my graph looks like this, all right? So here's 9, and then it increases by 1/3. So it goes over 1, up 3, right? I get a point somewhere like that, and my graph is essentially going to look like this. So are all the y values less than 0? No, because there's y values up here that are positive. Are all the y values greater than 0? No, because there's ones down here that are negative. Okay, so these two are out. If x is less than 0, so if x is less than 0, somewhere over here, are the y values all the ways less than 0? No, there's some that are greater than 0, like this guy. Okay, so that's out. And if x is greater than 0, if x is somewhere on the right, is y always greater than 0? Yes, it's always above the x-axis. This is choice 4. Okay, for 481, we can just type that function in. Okay, let's go up. Let's change this to 5 to the x. All right, and we're going to go back and go to zoom in a standard. So we'll get to see this. And we can see that as the graph is going to increase, and as it gets this way, it gets closer to 0. Remember, that's called an asymptote. It gets closer to 0, but it actually doesn't become 0, but it gets really, really close. So this is going to be everything greater than 0. Y has to be greater than 0. Okay, remember, range is the y values. What's the domain of relation? So just pick the x values out. We don't want to repeat, so we don't want to list like 4, 1, 0, another 1, another 4. This is already gotten, and that's already in there. So it's just 0, 1, and then 4. I'm not going to include the 1 again because I already have it. 484. If the domain is given, then the range is. Now, one way to do it is just to plug in. So 2 times -2 squared minus 8, then 2 times 3 squared minus 8, okay, and 2 times 5 squared minus 8. So this is essentially 8 minus 8, which is 0. This is 18 minus 8, which is 10. And this is 50 minus 8, which is 42. So I can see that I'm going to end up picking this one. Your other option is just to use your calculator and essentially just do a graph. Okay, so this is x squared, sorry, 2x squared, right? All right, minus 8. And then I can go to tab, and I can actually check out, right? -2, 0, okay, 3, 10, and 5, 42. So I can just use a graph and check the table for that. Which domain would be most appropriate? So we have a household income or online devices and the number of people in the household. So as the number of people go up, number of devices would go up. But what would the domain be? Like, can you have a negative amount of devices? And the answer would be no. Integers include negative numbers, so those are out. Okay. Whole numbers right, are numbers like 0, 1, 2, 3, 4. So this would be okay to pick here, right? Integers include negative, negative 1, right? 0, 1, okay, 2, right? Those are no-goes. We don't want to pick that. All right. Whole numbers are the 0, 1, 2, so that's okay to pick. Irrational numbers we would not want to pick, okay, because we're talking about decimals and also negatives, which is no-go. And rational numbers also include fractions and decimals, so we don't want to pick this one either, okay? So we would pick whole numbers because we would want to use whole numbers here, 1, 2, 3, 4, and no negatives. Construction company, F of P, where P is the number of people, and then the other one is money, but that relates to F of P. What's a domain for this one? So the number of people. Remember, domain is the X values, so that's the number of people, and same thing. Positive integers would be okay. Positive real numbers would not be okay because this once again includes decimals. Both positive and negative. Negative's a no-go, and we don't want any negatives here either. So we're using positive integers. The store sells frozen yogurts. It costs in dollars. What's an appropriate domain? And the answers are over here, by the way. Okay. So same thing. If we're buying frozen yogurt, we can have decimals representing the weight. So the weight in ounces. This is okay to have decimals here and fractions. You can have a fifth of an ounce and a sixth of an ounce. So the integers would not be okay, once again, because those include negatives. Rational numbers would be okay here, or actually would not be okay because once again, that includes negatives, okay? Non-negative integers, this might be okay, but there's no fractions. So this really isn't the best option, okay? So I should say not best, but not best option, okay? But non-negative radicals, this would be the best. This is okay to use. It's got decimals, right? Doesn't just have to be whole numbers. This is essentially just whole numbers only. All right. On to the next page, people. Types of functions. So there's linear functions, exponential, quadratic, square root functions, cube root functions, and absolute value. Linear functions, by definition, have an equal increase over equal intervals, which basically means as I go over 1 in the x-coordinate, I'm always going to increase by the same amount in my y, okay? So it's the same x and the same change in y. If you look at exponential, it's an unequal increase, meaning as I go over 1, I'm always increasing technically by a different amount, okay? The amount that I'm increasing by, you can see right here, is actually going to get smaller, smaller, and greater. This is multiplying and dividing by the same amount. So in exponential, I'm always multiplying by like 3 to the x would be times 3 times 3 times 3 times 3. Where adding and subtracting by the same amount is linear. Quadratic, once again, as I go over 1, the amount of increase I have is going to keep going up and up, all right? For square root functions, it's the same idea here. As I go over, okay, the change in y is going to be a little bit different every single time. And the same, and then for absolute value, actually the increase is equal. So it's an equal increase for the as x increases, y increases by the same amount. All right. So for 498, we want a linear relationship. So we want to look for the same increase. So you can see as we go through the first one, I'm going up 1, then I'm going up 3, 5, and 7. So this does not work because it's not an equal increase. Here I'm going up by half, then 1, then 2, then 4. So that's not the same. Here I'm going up by 1, 1 looks okay, but then 7, right? And then this doesn't make sense. But here we can tell we're basically going up 2, okay, up 2, up 2. So this is going to be a linear, all right? And then we can consider the pattern on this guy. And we can even do this with like an XY chart here, okay? So as x is 1 in the first graph, all right, there are 2 blocks. Then the second pattern, as x is 2, now we have 4, and then for 3, we have 8. And you can see, how do I get from 2 to 4 and 4 to 8, right? I'm essentially just multiplying the y values times 2, okay? So this would be an exponential choice here. And then we would want to use our pattern. Okay. Now, technically, what we actually want to put here is that this is a sub 1. Okay, this is the first graph. This is a sub 2. Okay. And then this guy would be a sub 3. All right. So for the nth pattern, we want a sub n, right? And now we know that it's just equal to times 2. So it's essentially equal to 2 to the n. Or sorry, yeah, 2n. So it's the, all right, and we can actually come up with, or it's an exponential. So it's 2, not times, but to the n, okay? And we can actually do that on the calculator as well. So we can go to a new document. We're going to open up that list and spreadsheets page. We're going to title, okay? And then we got our 1, 2, 3. We got 2, 4, 8. And we're just going to do a exponential regression. So statistics, calculations, exponential regression. We're going to choose our columns. So this is x and y. And then we can see it's a, so it's y equals a to the x. So it's 1 times 2 to the x, or to the n here, because we want to use it to the nth pattern. Okay? 501 shown below. In a petri dish, Rachel wants to model this with a linear function. Mark wants to use an exponential. So which is better? So we technically just want to look at the difference here, right? 280 minus 220 is essentially a difference of, where do we go? And all right, we're going to pause this while we get that back. All right, we're back. So we can see the difference between the 280 and the 220 is essentially a change of 60. Okay, from the 350 to the 280 is essentially 70, right? From the 350 to the 440, and we can actually subtract this, right? This is going to be a change of 90. So this really isn't necessarily appropriate. It's kind of interesting. Is it linear? I mean, we're technically just going up by 10 more each time. So it's kind of interesting how that works. What we can do is we can do a little regression here. So let me get the calculator up for a second here. And then because of this, right, so if we get our calculator up, we can take a look at it. But essentially, remember what we talked about. If this increases at a constant rate, we're going to use linear. But in this case, we want it to be exponential because it doesn't increase by a constant rate, all right? If you were to take what we just did, we can undo this, okay? And we can say we want to go for 5, 6, 7, 8, 9. And I mean, I'm not even going to use all of them. I'll go to 5 here. So it's 220, 280, that's 350, 350, okay, 440, and then we got 550, okay. So if I were to do and even just insert a document, right, and do the data statistics, I can choose my X and Y here, and you can actually see, right, the increase, it's increasing. It's not making a straight line here. So I wouldn't want to pick a linear. I would want to do an exponential. So we would just put down an exponential, since the increase is not the same. Okay, or as X increases, the Y value does not increase by the same amount. Which scenario represents an exponential growth of 2? So 2 gallons per minute, this would be linear because it's the same no matter what. 6 inches per week is linear. Doubles its population, that's where we're multiplying, so this would be 1. And then distance from garage at a constant speed, that's linear. Okay, so it would be choice 3. Fast model exponential. Doubles, that's exponential. Okay, 1 inch every 4 days, that is not. Declines by 5% every 3 years. We're multiplying by 0.05, so this technically would. So we would want to choose 1 and 3. Okay. By 5%, this by means multiplication. So that's how I know we're going to be picking that one as well. Okay, transformation of functions. Remember, if we add to the end of a function or subtract, it's going to go up or down. If it's inside the parentheses, it's going to go left and right. And remember, it's plus, it actually moves to the left, and minus goes to the right, okay? If you put a minus in front, it reflects over the x-axis. A minus inside reflects over the y-axis. And then if you put a number in front of our function, like f of, if we want to put like a, remember our a x minus h squared part, this a is going to vertically stretch it or move it closer to the y-axis or closer to the x-axis, okay? If it's greater than 1 or a fraction in between 0 and 1. So for 529, right, describe how the graph moves. So b of x, we can see the minus 2 here, means we're going to shift right 2 and then down 3. We're going to want to state that. Graph is going to shift right 2 and then down 3. All right. The next question is a little variation of it. Which statement is true about the quadratic functions g of x and f of x? Here we can see this is a parabola. It's going to be concave up, okay? And the vertex is actually at this point. So it's at the point 3, right? 3 to the right, and then 2 up. This vertex, okay, is at the point 3, -5. So do they have the same vertex? They do not, okay? Do they have the same axis of symmetry? They do. The same axis of symmetry is the same. That's the x coordinate of the vertex, okay? And what I would probably do is go graph, and you can check out what the zeros are going to be. Okay, this one has a 0 at 4, and make sure to see if the other one also has a 0 at 4. All right. Which quadratic function has the largest maximum? So same thing, we're going to want to graph these. We're going to want to compare. The maximum value in the graph is this y value. So I can see the turning point here is in between these two. So it's something like 3.5. So this is bigger. And then we can go graph. Remember, if we wanted to do -b over 2a and plug in, but I would probably just want to graph this and actually visually see it, okay? So no, graph, so it's -x squared, all right, plus 2x, and then plus 4. We're going to check that we can see right here, so we can do menu, okay, analyze graph, and we're going to choose your maximum value, and there we go, it's the 0.15. So these have the same actual here, all right, and if we check the other one, all right, so let's just do another graph, so we'll do tab, all right, and that's -x minus 5 squared, and then plus 5. All right, ooh, same thing, okay? So we can actually check those out, largest maximum value over the set of real numbers, and we want to pick one accordingly. Oh, actually, these guys, notice are both 5. So this one is going to be somewhere in between that and a little bit more. So we would actually want to pick choice 2. It's actually going to be a little bit more. It's in between those two. All right. Greatest y-intercept. So we can count here 1, 2, 3, 4, 5 on the graph here, right? 1, 2, 3, 4, 5. So this is the y-intercept of 5. This y-intercept is 0. If we solve for y here, we're going to get y is equal to -2/3 x plus, we're dividing by 3, so plus 4, and then has a slope of 2, passes through the point 1, -4. So on the graph, 1, -4 is down here, right? It has a slope of 2. So if we went over 2 and up 1, or up 2, you can actually graph for points here, right? Slope of 2, so up, or in this case, we want to go up 2, right 1, or down 2, left 1. So our line is actually going to be hitting somewhere down here. It's going to have a -1. So the greatest y-intercept is going to be the graph, okay? It's going to be the graph, because it's got a y-intercept of +5. All right. Which statement about these functions are true? So the graph below, is there a graph below? There is not a graph below. So don't even worry about this one, because the graph's not there. All right. And that's it for tonight, guys. Have a good night. We'll see you later.